All right, good afternoon, class, or well, professor. This is going to be my presentation on roots and radical functions in the real world, and then my name is Logan Poole. So what are roots? Roots are the inverse operations of exponents. So for instance, a of n is equal to b, then a is equal to radical n b. So as you can see right here, it's just the n is just going to go into the where the square root is. Radicals are just expressions that involve roots. This is the radical symbol right here. So radical 9 would just be 3, and then 3 radical 8 would be equal to 2. So that would just be 2 times 2 is 4, times 2 is 8. So 3 sets of 2's. The difference between a normal radical and a function is just if the variable is inside. So this is the formula for that. F of x is equal to radical x. In the real world, though, they show up in physics, engineering, when involving areas and volume, and also show up in finance, biology, and computer graphics. So the history of roots, this is rooted all the way back into the Babylonian times and the Greek times. It goes as far back as 1800 to 1600 BCE, and there are records of roots being shown on stone tablets. This is just an image of one that was found. This is a right triangle, and it's a value of radical 2 in Sexa. I can't even say this. This is such a hard word to pronounce. I was actually researching how to pronounce it, but I couldn't find it. I think the best I was able to find was sexagismal, and it goes all the way to 6 decimal places over. Eventually, as time went on, though, the radical symbol evolved to what we commonly have as the radical symbol, and this was in 17th century. Christoph Rudolph. Then about 100 years later, Rene Descartes helped standardize it in algebraic notation. This is important because it helps mathematicians express equations concisely. So the mathematical concept right here, this is just a graph of a radical function, radical x minus 2 plus 3. So starts right here, it goes, shoots all the way to the right. I like to refer to it as the shooting star method because it's kind of like a shooting star in how it's represented. And then when calculating, you need to use the product rule. And then this is the formula for that. And then an example of it would be radical 50 is equal to radical 25 times 2. And then since 2 can't be simplified anymore, you can just do 25. You have to radical it. So radical 25 is 5. So the final formation is 5 radical 2. And another thing is to match the exponents together. So for this one right here, radical x, radical 18x cubed y squared. So if we're going to go ahead and simplify that, we need to first break it down. So radical 9 times 2, because 18 is 9 times 2. And then you're going to have radical x squared plus x, multiply that by radical squared. And then after you get all of this together, it's just going to be 3xy radical 2x. And that's because radical 9 is simplified to 3. 2 can't be simplified anymore, so it's going to be inside. Then x squared. You need to have the x on the outside. This x can't be simplified anymore, so it's just going to go right here. Then the y squared is just y, so it goes right there. Then there's change over time. Al Quasamini played a crucial role in expanding algebra as a whole, and his book he treated algebra more like a discipline, and he helped with solving linear and quadratic equations using his own method, which he called restoration and balancing. Al was also a key player in transitioning from geometric roots to algebraic roots. I also, before we continue, I just want to apologize for getting all of these names wrong. At least I'm trying. It's the thought that counts. Even though Newton is more famous for his calculus work, he helped formalize roots as functions rather than just being the side length of a square. These were two key players in changing roots and radicals as they evolving into what they are now. The history shows that in 1200 it was a hook-like, but in 1525, first print of the commonly known radical, then the vehiculum was added later, around 1637. What I wanted to represent here was the change that radicals had to go through. In the beginning, they were just hook-like, and eventually, as time gone on, hundreds of years, it became what we know now. Now I want to go into how it's affected architecture and engineering. So in both of these, they use the Pythagorean theorem, which leads to radical expression. And architects and engineers use this when they need to calculate distance, slope, supported lengths. When they're calculating parabolas and arches, they use radicals. So in all honesty, the world wouldn't be as advanced as it is if we didn't know radicals because bridges and buildings and whatnot would just start collapsing. Next, I want to go into medicine and biology. The reason that radicals are used in medicine is when calculating how much each dose of medicine that a patient should have. So without it, we would be either underdosing or overdosing patients. We calculate this by doing the height and weight, and then we divide it by 3600, and then all this is inside of a radical, and then we get the proper amount per person, give or take, obviously. Next one right here, I just wanted to give a graph that represented the comparisons of these radical functions right here, radical x, and then f of x is equal to cubed x. So obviously they are very similar, yet also different at the exact same time. So radical x is going to be the red one, and then cubed x is going to be the blue one right here. Next, I want to go into how modern technology uses radicals. So radical functions are the only reason that 3D modeling actually works. This is only because of the Euclidean distance, calculating using square roots. And then this is the formula right here that we use. And then the graph, right, well, the diagram right here, this just represents how radicals are used in three-dimensional objects. And it helps when measuring the distance. And then the applications that these used for are when image processing, 3D design, robotics, and augmented reality and virtual reality. And then I want to go into the biblical translation, who this is Isaiah 40:12, who has measured the water in the hollow of his hand and marked off the heavens with a span and closed the dust of the earth in a measure and weighed the mountains in scales and the hills in a balance. So this verse shows the infinite wisdom and how much precision God has. He has to measure he has to measure everything with perfect balance. Math is similar, just in a qualitative form. Mathematics as a whole shows how symmetry and geometrically harmonious God's creation is. Christians like Isaac Newton showed us that scientific discovery and faith can go hand in hand, but math as a whole should be used to worship as a whole. So, in summary, roots and radicals have been a mathematical concept and have has consistently evolved from times in Babylon all the way to the 17th century when scholars like Al, Rudolph, and Socrates started expanding on them and truly began understanding what they were. They're the foundation of solving equations, modeling relationships, and connecting theories. This world as we know it wouldn't be the same without them. Buildings and bridges wouldn't have been built, nor would doctors been able to prescribe the proper medication to patients. Most importantly, mathematics represents the beauty and design of God's creation. Specifically in Isaiah 40:12, articles aren't just a mathematical terminology, still it reveals divine harmony and an understanding beyond the physical world. And then these were the sources that I used in my slideshow. And thank you guys for watching.